In section 7.2, we're going to describe the formation of covalent bonds, and then we're going to define electronegativity and assess the polarity of covalent bonds. So covalent bonding is the result of atoms sharing a pair of electrons. Okay, so the electrons get shared between the two atoms participating in the bond. Electrons in a covalent bond are equally likely to be close to the nucleus of either atom participating in the bond. So this is what makes it distinct from ionic bonding, where an electron gets associated with one of the nuclei over the other. Covalent bonding occurs between elements with fairly close ionization energies and electron affinities. So this is what leads to covalent over ionic bonding. Sharing electrons still results in atoms being isoelectronic to the nearest noble gas. So an example of that is when two hydrogen atoms share one electron to form H2, the result is isoelectronic to helium. So they're still doing it for the same purpose, to get a stable electronic configuration. When covalent bonds form, the outer orbitals of the atoms overlap, and this is going to release energy. The attraction of a shared electron to the nucleus of the atom it is being shared with is balanced with the repulsion of the two atoms' nuclei. So the two nuclei are positively charged. They want to repel each other, but we also have energy being released when these electronic or orbital overlaps start happening and they start sharing these electrons. So there's a sweet spot between them where they're not repelling each other too much, but they're still getting the benefit of this energy that's released. The length of a covalent bond is determined by the distance between nuclei that results in the lowest potential energy. So what happens is, if we plot out this energy, so here we have two hydrogen atoms that are not bonded at all. They start to get closer and closer together. They start to overlap their orbitals, and energy starts to get released. And that energy is released. It's released. You get a lower energy atom here, or molecule that's forming. And then eventually you get to this sweet spot, and that's the distance that it's going to want to maintain between those two nuclei. If we go any closer together, the two nuclei are going to repel each other, and then eventually that becomes very improbable, right? Where the nuclei are almost right on top of each other. And then they're not going to be released and become separated again without the input of at least this much energy. So earlier in the term, we saw that some reactions are going to be exothermic and they're going to release energy, while others are going to be endothermic and going to wind up absorbing energy. We can now see that the energy absorbed and released is due to the making and breaking of chemical bonds. So when we make a chemical bond, we're going to release some energy. And when we break a chemical bond, that's going to require some energy. And here's an example where we can see that when we have H2, like in our previous example, and we break that up into two free hydrogen atoms, it's going to require 436 kilojoules of energy. But when we have two hydrogen atoms and we form an H2 molecule, we are going to release 436 kilojoules of energy. So the difference between pure and polar covalent bonds. Covalent bonds formed between identical atoms share electrons equally. Okay, these are called pure covalent bonds. So the electrons are not going to be associated, they're not going to be held any closer to one of the atoms than the other because they're identical. And examples of that are like our diatomics, like H2, Cl2, N2. When the two bonding atoms are different, electrons are attracted more to the atom with the greater electronegativity. Okay? This attraction leads to a shift of electron density around the bond. So that means that the electron starts to be associated more with one of the nuclei over the other, and we call this called the electron density. So this is like a probability model of density, where we have the electron just more often being found in one region over another. This unequal distribution of electrons leads to polar covalent bonds. The unequal distribution of electron density result in a partial negative charge, which we're going to abbreviate with this lowercase sigma negative sign to indicate that that's a partial negative charge on the atom with greater electronegativity. The partial positive charge, sigma plus, forms on the atom with the lower electronegativity. The greater the difference in electronegativity between the two bonding atoms, the greater the magnitude of the partial charges formed. So let's see how we're going to write that out. Here we have an example of HCl. Hydrogen is less electronegative than chlorine. And we can see we have a partial positive charge on the hydrogen and a partial negative charge on the chlorine. This here is indicating that there is a push of electrons towards chlorine. This is what is known as a dipole. And the obvious question here is how do I know how electronegative something is? Well, this has already been calculated for all the elements, and you can see in this periodic table here where all the electronegativities lie. And you can see that in general, on the left-hand side, we're going to see low values, so not very electronegative atoms. And over here on the right-hand side, we're going to see higher values, more electronegative, which makes sense because we know that over here, these like to form anions, and these guys like to form cations. So these guys like electrons a little bit more than these guys on this side. We're also going to note that electronegativity tends to go down. As we go down the periodic table, we have larger atoms, and there's an effect called electronic shielding that keeps these from being, that kind of suppresses the electronegativity of the elements at the bottom of the periodic table. So electronegativity looks a lot like another quantity we've studied called electron affinity. These two quantities are in fact related, but have important distinctions making them unique. Electron affinity is a measurable physical quantity, specifically the amount of energy released or absorbed when a single atom in the gas phase acquires an electron. So we can measure electron affinity. Electronegativity is not measurable. It is a calculated dimensionless quantity that describes how tightly an atom attracts bonding electrons. So it only doesn't work with electrons that it already has. It's only in the electrons that it can gain through bonding. So the absolute value of the difference in electronegativity of two bonded atoms provides a measure of bond polarity. And that's going to dictate the bond type. So what winds up happening is that when there is very, very little difference in electronegativity between the two atoms, you wind up with this pure covalent bond where everything is essentially shared between the two atoms. Once you get to a difference of about 0.4 to 1.8, you're going to wind up with a polar covalent bond. And then once it exceeds a difference of 1.8, that's when you're going to start to have ionic bonds form. And we saw that those are going to behave differently, where now an electron is associated almost entirely with one of the nuclei over the other. And finally, we'll stop by acknowledging Linus Pauling a little bit. His initial work in 1954 that won him the Nobel Prize really cemented the way for our understanding of how chemical bonding works. He was a really quirky guy, really brilliant. He did win the Nobel Prize twice, once in chemistry, and another time he won a Nobel Peace Prize for his for speaking against like nuclear weapons and weapons of mass destruction and stuff. He famously did a lot of little kind of quirky, weird things. He was one of the first proponents of taking vitamin C. He took upwards of 1 gram of vitamin C every day, which at the time when he first started doing it, probably still isn't a good idea. But when he first started doing it, they said, well, you're going to die right away from doing this. And you can see that he actually lived to be 93. And he died fairly recently within my lifetime in 1994.